The Great Pyramid's machine-level precision. Stand at the southeast corner at dawn. The shadow rides the casing bed like a blade on glass. The first stake is simple. If Old Kingdom teams did this with copper, stone, and time, then we've underestimated everything downstream. Surveying in Mesopotamia, masonry in the Andes, astronomical planning in Greece. Because here, precision isn't decorative, it's structural. Action first. Forget the missing smooth white casing. A few stones at the base still tell the truth. Joints so tight a blade barely whispers across them. On the ground, the foundation is leveled to within millimeters over a 13-acre footprint. The sides don't just aim north, they cling to it. The orientation error is tiny, minutes of arc, not degrees. That demands a method, not luck. Walk the perimeter and the geometry stays stubborn. The side lengths match within inches across hundreds of feet. Corners, true right angles, don't drift more than a human hair per meter. Inside, the king's chamber sits in granite that laughs at copper saws. The sarcophagus box. Its interior corners are square in a way a field-worn chisel doesn't normally deliver. The chamber roof uses stacked relieving blocks, massive granite beams layered to redirect stress around an empty room, which means someone modeled loads in their head. Human angle. This isn't a wizard in a robe, it's foreman counting stones and bad days. Picture the survey team sleeping on the site, correcting lines at first light because heat shimmer ruins them by noon. Imagine the quarry boss deciding whether to gamble on a bed that might fracture halfway through a cut. There's a scribe keeping tally of transport crews, water, and wood. Behind every joint that seals tight, there's a worker who shaved that last fraction because the master would reject a whisper of daylight. Now the complication. Precision outside is one thing, inside it turns weird. Air shafts, narrow, straight, and angled, strike towards specific regions of the sky. The corridors hold dimensions that seem to carry ratios, not random lengths. If you move through the grand gallery, the corbelling stacks with consistent offsets as if pulled from a template book. These are machining behaviors, repetition, standard offsets, predictable fits. Let's give the counter-arguments their due. Skilled labor plus time. Absolutely. You can turn soft limestone into a mirror with sand, water, and enough hands. You can true lines with solar observations and clever sighting tricks. Over decades, error can average out. But the tolerances here are repeatedly smaller than the error budgets we'd expect from ad hoc methods. It's not that perfection appears everywhere. It doesn't. It's that the system shows selective excellence where it matters most. Orientation, base leveling, critical joints, high-stress spans. Meanwhile, something else is happening in the stone itself. Granite for the king's chamber comes from Aswan, far to the south. Transport isn't just a feat, it's planning. Those beams had to arrive in sequence. If one cracked, the schedule collapsed. The relieving chamber stack is a commitment. You don't layer unneeded mass unless you're countering a known risk. That's engineering judgment in advance, not patchwork after failure. Here's where it gets thorny. Tool marks and residues tell a mixed story. You can see copper saw striations paired with abrasives like sand. You can replicate straight cuts with grit-charged cords, but replicate the interior of that granite box to the same squareness and finish. Modern attempts get close, then drift. The fit you feel running a fingertip along the seam doesn't lie. Personal test, even a tiny ridge catches skin. At Giza, many don't. The alignment to true north needs a way to find north that beats a wandering needle. North is a trick of the sky. Shadow methods work, star transits get you closer. The likely approach, observing circumpolar stars crossing a plumb line, correcting with repeated trials to shrink error. That demands time windows, clean horizons, and patient nights. It also demands that someone set a tolerable error. That's the part that reads like a speck. This wasn't close enough. This was within a limit. Consider base leveling. 13 acres, you don't eyeball that. Water trenches, sighting frames, repeated fills and drains, then cut, check, repeat. The last check happens when the first course ties. If a corner lifts, you see it immediately in stone behavior. The masons didn't see it, not because it wasn't there, because they'd already killed it. Now the big why it matters. If this level of planning and execution sits at the core of the Old Kingdom's signature monument, then their knowledge networks were more than local tricks. Surveyors were trained to a standard. Quarry teams followed marks that meant the same thing from Aswan to Giza. Scribal math tracked volumes and angles with rules you could hand down. That implies schools, pattern knowledge, maybe even reference tools we haven't found because they were perishable. Wooden squares, string templates, papyrus guides. There's one more headache. The pyramid's precision clusters. Not every block is a marvel, many are rough. That's how modern projects look. 2 critical areas get the tight tolerances, non-critical areas take the slack. That's a mindset. Assign your best people and your time where failure would cascade. It's logistics intelligence, not a miracle. The easy answer says, thousands of workers, decades of effort done, true and incomplete. The harder answer asks, where are the training artifacts? Where are the standard sticks, the gauges, the pattern blocks? If they were wood and fiber, the desert erased them. But their ghost remains in the stone. If precision is a one-off miracle, fine, write it off as a cultural summit you only hit once. But Giza isn't an isolated mountain. It's a signal. And if you're hoping it stands alone, Bolivia ruins that hope. Puma Punku's interlocking stones. While the desert light at Giza sharpens edges, the Altiplano wind does the opposite. It rounds them, scours them, tries to erase intention. And yet at Puma Punku, intention refuses to fade. This is the place where the word primitive stops doing any useful work. If tight joints at Giza were a standard, here the standard becomes a geometry lesson. Walk the scatter field. It looks like a stone factory had its shelves kicked over. H-blocks lie on their backs like letters that fell out of a page. Each face isn't just flat, it's disciplined. Right angles repeat inside right angles, edges break into steps, and along the sides you find consistent slots, mortises, and shallow drill-like recesses spaced as if by a jig. When two blocks meet, they don't just touch, they interlock. No mortar, just confidence. Stakes up front. If a mason trained with ad hoc habits made these, then trial and error produced repeatable modular parts across dozens of pieces, parts that still line up after earthquakes, looters, and centuries of frost. That means templates, and templates mean a shop culture, not one weekend of inspiration. Action, the andesite is the problem child, harder than the red sandstone foundations, stubborn on a tool edge. Copper alone loses the fight, so the team that shaped it used abrasives. You can cut straight lines with a grit-charged cord. You can flatten with grinding sand and patience. You can snap edges crisp if you control your pressure and your checkpoints. The signature here is repetition. Channels that run inside H-block webs match across separate pieces. Corner notches mirror depth and width. The H itself isn't random flair. It's a structural solution to lock members while controlling load paths, the way a modern connector spreads force. Human angle, picture the template maker, the most valuable person you'll never hear named. They guard a handful of boards or strings, reference lengths and angle jigs used to lay out each block. Apprentices drag cords through slurry all day, checking the sound a surface makes when a straight edge kisses it. The foreman calls a reject if a notch misses by a finger's width. That's cost. That's pride. And someone is managing the sequence because interlocks only work when placement order is correct. Materials question. Andesite doesn't reward the sloppy. Try pushing a soft metal chisel into it without grit and you bruise, you chip, you wander. Add sand and you can abrade grooves clean. Where rivet-like cramps tie stones, analysis at nearby Tiwanaku shows ternary bronze clamps, copper with arsenic and nickel, poured into dovetail slots to stitch courses. The clamps are gone at Puma Punku, but the slot shapes argue the habit traveled. Metalwork and stonework speak to each other here. Theories versus tests. Replicas have been tried. With simple tools, you can make a block with an H, silhouette, and crisp edges. You can carve interior channels. What breaks modern attempts is standardization across dozens of parts, the way widths, depths, and step heights align without drift. Where the copies fail is consistency of offset and the sharpness of interior corners under load. The real stones maintain 90-degree corners inside complex recesses with minimal spall. That takes staged grinding and polishing, with checkpoints you don't invent on the fly. Impact, standardized interlocks change everything. They imply measured repeats, not close enough. They let you predict how a wall behaves in wind and tremor. They let a site scale labor, hand one team the template set, and they can make members that fit a plan they've never seen in full. That's modular thinking. That's industrial behavior before factories. Meanwhile, something else is happening on the ground. The sandstone foundations carry channels and cutouts that route water. The andesite blocks perch on those beds like precision parts on a base plate. It suggests a drainage logic, a load logic, and perhaps a ritual logic stacked together. Purpose arguments multiply, gateway, shrine, calendar, but beneath the debate sits the same quiet fact. Whoever ran this site had a spec. Let's handle the pushback. People say straight lines don't prove machines. Correct people with time and grit can make straight lines. They say photos exaggerate tolerances. Fair angles compress edges, but stand next to an H-block and run your hand along a slot. You feel the absence of waviness. The reveals sit at uniform depths. The drill-like pits, some align, some don't, tell you there were different teams, different days, but a shared intention. The variance lives in the finish, not the layout. Comparisons help. At Inca walls, polygonal blocks key in with remarkable fit, but their surfaces undulate by design. At Puma Punku, the style is the opposite. Planar faces, rectilinear cuts, interior mortises that feel pre-specified. It's less sculptural, more mechanical. Impact immediate and wide. If this is the Tiwanaku world in the 6th century, they're not guessing. They're training. They're moving in step with surveyors who can keep a baseline straight over real ground. They're teaching apprentices to hit tolerances, not just shapes. And that spills outward. Quarry selection, transport slings that don't chip edges, staging areas that protect heiresses from damage. Logistics upgrades are baked in. One more human moment. A mason tests fit by tapping 2 stones together. The sound sharpens when the contact area increases. At Puma Punku, that sound would have been a language. When the note rang right, the stone advanced. When it thunked, the rasp came out again. Precision is one thing. Here the mindset is the tell. Someone brought templates to the mountain. Someone enforced them, and the blocks still obey. Baalbek's Trilithon and the stone of the pregnant woman. If precision makes you question the workshop, Baalbek makes you question the yard. Here the problem isn't how clean the joint is. It's that the joint lives in a block heavier than a blue whale. This is where you can't lift that, stops being a taunt, and becomes a design constraint. Stakes first. If pre-industrial crews moved and placed blocks in the 751,000 ton range, then our timelines for logistics, traction, and risk management are off. Not by a little, by orders. Because once you can reposition 1,000 tons on command, every other site's massive looks small. Action on the ground. Walk the western retaining wall of the Temple of Jupiter and the Trilithon stares back. 3 limestone blocks, each roughly 19 meters long, 4 high, 3.5 thick. Stacked with joints so controlled you could hide your hand in the seam and still feel stone-on-stone intimacy. Beneath them, smaller foundation stones still hit 300-400 tons. Up the quarry road, the stone of the pregnant woman lies where it was cut but never pulled, dimensions that push the meter into 4 digits of tons. Nearby, another monolith, even larger, sleeps half-buried. These aren't showpieces, they're project leftovers and milestones. Now the sequence that matters. The quarry sits upslope, which means gravity is both enemy and tool. You can loosen a block with trenches, undercut it, crib it with timbers, then lever and slide it on a prepared bed. Slope helps start motion. Control keeps you from losing the sight. That suggests a choreography. Quarry crews cut with pre-planned sled clearance. Road teams grade a path. Wall crews set bedding courses wide enough to accept behemoths without edge crumble. Human angle. Picture the foreman at dawn staring down a block that could kill 30 men if a crib snaps. His calendar isn't philosophical, it's seasonal. Dry months give traction, wet months sink sleds. He's rationing rope because fiber weakens with knots and humidity. He's counting oxen or men or both, and he's talking to the carpenter about sled runners and sacrificial planks that will turn to pulp under load. Every meter costs wood. Every pause risks embedding the block in its own crushed bedding. Comparative loads clarify the gap. Egyptian obelisks hit 300-400 tons. Roman lifting culture handled multi-ton columns and architraves with treadwheel cranes and gangs. But 1,000 tons is outside crane logic. You don't lift it, you lower friction. That points to sled and rail systems, lubricated clay, crushed stone beds, oiled surfaces, or wetting strategies to keep dust from turning to grit. Add in lever banks where long timbers and fulcrums walk a block sideways into final seating, a few centimeters at a time with chocks catching the backslide. The integration argument gets louder when you look at the layers. Roman temples ride the terrace, but the most massive courses under them may predate or represent a different construction episode. Styles differ, stone sizes jump scale. The overlay says reuse, respect, or both. Either way, the lower platform reads like an infrastructure decision. Make a base that won't move, then build forever. Pushback deserves oxygen. Some say the blocks were never truly moved far, that they were cut, slid a short distance and jacked into place with earth ramps and patience. That's plausible, and it shrinks the feet from drag across miles to control for meters. It doesn't erase the problem, it restates it. Controlling 1,000 tons for meters without catastrophic failure still demands a playbook. What did that playbook include? Ropes plied into cables, possibly thick as a wrist, sleds with bronze-shod runners or carefully pebbled beds to avoid suction, rollers for smaller pieces but likely not under extreme weight where crushing turns timber into wedges, teams with poles to keep alignment, signal flags or horns so 100 pullers ease in unison. The physics isn't exotic, the system discipline is. Now the telltales. At quarries near Baalbek, you see draft lines, undercuts, and relief trenches that let a block sit on a ridge before release. That ridge acts like a hinge. Once a sled sits beneath, you cut the hinge and transfer weight to a platform already braced. If a corner chips, the bedding fails, so crews likely dress the receiving course in situ, checking high spots with straight edges and pigment, the way millwrights blue steel. Impact construction sequencing here implies an early decision. Oversize the foundation to move stress into the earth, not the wall. The Trilithon locks a retaining structure, it's not a vanity belt. That means the planners forecast lateral loads, soil pressure, quake impulse, and chose mass as insurance. They didn't need mathematics on paper to know that. They needed memory of collapse, which implies earlier failures we don't see. Meanwhile, the calendar bites. Move in the cool, avoid midday expansion. Keep fibers fresh, store coils out of sun. Replace sled shoes before a burnished runner becomes a skate and surges. The risk envelope is narrow. A single uncontrolled slide could shear a crew, splinter timber, and crater months of prep. The integration question returns. Roman overlay versus deeper megalith. If later builders chose to mount on that terrace, they were endorsing ancient engineering by action. You don't set Rome's grandest eastern temple on bad bones. You set it on the one thing in the valley that won't flinch. So could they move mountains? They did. Slowly, stubbornly, with physics anyone can test and logistics few can master. And if 1,000 tons can be persuaded to edge forward on command, then the sky might be next on the list of things they tamed. Nazca Lines and the sky problem. While Baalbek wrestles with gravity, Nazca argues with perspective. Out on the pampa, the world is flat, hot, and quiet.